Okay, today we're going to be looking at transforming a relationship to a linear form. So when we are doing experiments in science, we often do get experimental data with two variables, and we want a mathematical formula to describe how these two variables are connected. If we have a nice straight line, say we have a nice straight line like this, and we've plotted we get a nice, this usually within, when we get our variables, so they're x and y, and you're plotting experimental data, it's not going to fit exactly, so you do your line of best fit because there's always going to be different experimental errors involved. But you get a nice straight line, and it's nice and easy to find a relationship because that'll be, for a straight line, the general formula is y equals mx plus c, where m is the gradient and c is where it crosses the y-axis. However, the world of science and the natural world is not as nice and easy. More often than not, we'll have something that looks like this. And it's not a straight line, and it's not so easy to find the relationship between our variables x and y. We end up with a line which has a general formula more like k times x to the power n. Or y equals k a to the power x, where k, a, and n are all constants. Now what we can do is we can use logarithms. We can take the log of the y and the left and right hand side of these general formula, and we can then turn this into something that looks like this, and then plot that formula and get a straight line. How do we do this? So we're going to look at, let's get a new sheet up. So we're going to look at converting y equals a e b to the x, where e is going to be Euler's number, and a and b are constants. And we're going to convert it into the form y equals mx plus c. So what we do is we take our y equals a e b to the power bx, and we're going to take natural logarithms of both sides. So we will have the log of y, the log of a e to the power bx. And now we can use the laws of logarithms to manipulate this side. So we'll have, the log of a plus the log of e to the power bx. Now this stays as log of a plus, now the power law will bring the b down, and that'll be the log, natural log of e to the x, but that then just becomes x. So what we're just going to rewrite this, change the order. So we have bx plus the log of a. But if we look at this, now we're going to compare this to this. So we'll write this underneath. And what we see is the natural log of y is like y. We've got the gradient corresponds to b. X is still x. And the log of a is c. Now when we do this, it's important that the variables x and y in this part of the formula only contain the original variables x and y, little x and y. They must not contain any unknown constants a and b. So if you look here, x is separate from x, but log of y is y and the log of a is c. You don't have the mixing of the variables in any of the big Y and big X parts. And also constants M and C must only contain the constants A and B. So they can't contain, the same ideas here. You can't have the part like M here has to just contain the part B, and C only contains A here. There's no mixing of variables. Now let's look at an example. The variables x and y satisfy y equals a e to the minus bx squared, where a and b are constants. The graph of the logarithm of y against x squared is a straight line passing through the points 0.55 and 0.84 and 1.72 and 0.26. And we're going to draw a diagram. So what we want to do is find A and B. So we've got the graph of the natural logarithm of y against x squared, and then you've got these 2 points, 0.55, 0.84 and 1.72 and 0.26. So we have y equals a times e to the minus bx squared. And so we're going to take the log of both sides, natural log. Now we're just going to play with this with our power rules. So we'll have log of a plus the log of e to the minus bx squared, and we can use the power law to bring this down. Log of a minus the log of b, because the minus is going to come down and turn into minus, and then we can separate that out, but this is just going to end up being x squared because the log of e cancels that out. And that then gives us log of y is minus bx squared plus the log of a. So if we equate these out, this is y, this is m, this is x, and this is c. So firstly, we can work out m from the gradient. So we've got 0.26 minus 0.84, just using our gradient formula that we're familiar with from previous years. And that gives us minus 0.4957. And to 2 decimal places, that therefore means b would be 0.50. We've got the minus here, and the minus cancels, so b's that. Then we have, so if we take a point for y is 0.84, and that's equal to minus 0.4957 times x squared, which is down here, so that would be 0.55. Remember, x, this is plotted by x squared, so you don't need to square it, plus c, and that gives us c is 1.1126. I'll write this up here. So the log of a is equal to 1.1126. So if you take a is going to be e to the 1.1126, and we can just, and then so if you do that in your calculator, you'll get 3.04. So then we've got b, and a. Let's look at another example. So we have some data. We've got values for x and values for y. So 5, 10, 20, 40, 80. And the values of y are 2,593, 1,596, 983, 605, and 372. So this is experimental data that we've gathered from some experiment that we've done. So firstly, by plotting a straight line graph show that x and y are related by y equals k x to the power n, where k and n are constants. B, use the graph to estimate values of k and n. So firstly we're going to take this formula and we're going to take natural logarithms of both sides. And again we're going to manipulate this. So we'll end up with log n, the log of k plus the log of x to the n, which gives us the log of y is equal to n the log of x plus the log of k. And that then gives us our general formula, y equals mx plus c, where m is n, the log of x is x, too big x, sorry, and the log of k is c. So now we need to plot our points. So I've not got graph paper here, so mine's going to be a sketch just to give you an idea. So we've got the log of n, which is going to be our x's, and our log of y. So doing that, we have we're going to take the log of x and the log of y. Oops. And we'll get, so the log of x here would be 1.61, and just do that for each of the values. And then likewise take your y values and take the natural logarithm for them. Oh, this one out somewhere. Oh, here it's 6.89. This is 6.41 and 5.92. And then we're going to graph these. So like 1, 2, 3, 4, and 2, 4, 6, 8, 10. So for 1.61, it's going to be round about here. We'd have 7.86 about here. Then 2.3 about here. 3, 6 point. Maybe up a bit more there. I've not made these very nice at all. There we go. So we've got a kind of a straight line like this. So we'll then use our points here to get the gradient. So gradient is m, n. So the gradient m is equal to n. So we would take points from here. So we'll take you'd read so yeah, we'll read off values on here, but because this is not on, you need to get proper graph paper to do this. So if we're proper graph paper, we take 2 points and then you would get something in the region of this, minus 0.7. And then you would find k is going to be the point that it would cut the y-axis. So c is equal to the log of k, which is equal to round about 9. And then you would take so c must be the natural log, the exponential of 9, which comes out at about 8,100. So yeah, I hope that helps.